Hello everyone, this is your tutor AB and today we're going to be solving a problem from November 2018 IB examinations. This is a paper 2 SL question and it relates to the topic of work energy power in the mechanics chapter. So let's get started. The question: ion thrust engines can power spacecraft. In this type of engine, ions are created in a chamber and expelled from the spacecraft. The spacecraft is in outer space where the propulsion system is turned on. The spacecraft turns on from rest. And a key thing to know about these type of questions is they do give you more information than you actually need. So do scan the question to see what you actually need for the problem. So here they give you a diagram, and in this diagram you can see the motion of ions and so forth. The mass of ions ejected each second is 6.6 into 10 to the power of negative 6 kilograms, and the speed of each ion is 5.2 into 10 to the power of 4 meters per second. The initial total mass of the spacecraft and its fuel is 740 kilogram. I assume that the ions travel away from the spacecraft parallel to its direction of motion. An initial mass of 60 kg of fuel is in the spacecraft for a journey to a planet. Half of the fuel will be required to slow down the spacecraft before arrival at the destination planet. In practice, ions leave the spacecraft at a range of angles as shown, and they give you another diagram. See, there's a lot of information in this question. What do we actually need? Keep that in mind. Part A, 2 marks. Determine the initial acceleration of the spacecraft. Now, I want you to refer back to your data booklet. Do you have an equation such that you can solve for acceleration? Well, we have this equation from when we were learning Newton's laws, which is F is equal to ma. You rearrange it, you get F by m is equal to a, no? Now, how does this help us? How can we calculate the force at which these ions leave the spacecraft? Because the force at which they leave the spacecraft is also the force at which the spacecraft is thrusted forward. So acceleration of both the ions and the spacecraft would be equated. So how can we calculate this? Well, we can say force in your data booklet is also equal to, not force, right? Impulse J is equal to force delta T. This is an equation. This is the equation for impulse. An impulse is none other than the change in momentum. So we can say this as mv final minus mv initial. This is also given in your data booklet, the formula for linear momentum. So if we solve for impulse, what do we get? We get the momentum final is equal to the mass times velocity. Mass of what? The mass of the ions. So 6.6, let's just double check if I'm using the right mass of ions. Yes, 6.6 into 10 to the power of negative 6 times the velocity, which is 5.2 to 10 to the power of 4, and this thing minus the mass, the momentum initial, which would actually just be 0. Why? Mass is constant, but the velocity is 0 because the ions are initially at rest, as it states in the question. So minus 0, that gives us J. Okay, so if we put this on our calculator, right, what do we get? Impulse is equal to 6.6 into 10 to the power of negative 6 times 5.2 into 10 to the power of 4. So we get the impulse J is equal to 0.3432. Now, looking back at our question, we need to solve for the force, right? So we would again to go here, we can start over here. So if we say 0.3432 divided by time would give us force. But what is the time? Well, it's just going to be 1 second. Why? Because this is how much is ejected per second. So it is just divided by 1. So this is also equal to the force at which the ions are ejected out of the spacecraft. Now, using this force which we calculated, we can then solve for acceleration, because if you put 0.3432 over the mass, right? That's what we got here. Mass of the spacecraft, because we were calculating the acceleration of the spacecraft. Mass of the spacecraft will be 740 kilogram, as it states right there. So 740, right? We make sure all our units are correct, which they are. So if we solve this divided by 740, we get the acceleration of the spacecraft is 4.6 into 10 to the power of -4 meters per second. Meter per second square. Okay, so let's just write this properly here. Let me just lasso this. Move it right there. That's your answer. That's the acceleration of the spacecraft. Okay. Estimate the maximum speed of the spacecraft. Now, how do we solve this question? Let's think about it, shall we? Well, what could we do? Can we use momentum again like we did in the previous question? Well, why not, right? Because momentum is always conserved. So we can use momentum in this case. So how do we use momentum? Well, what we can do is say the momentum final is equal to the momentum initial. We equate the momentum of the ions to the momentum of the spacecraft and solve for maximum velocity. Now, what do I mean by this? We can say the mass of the electrons, which is 6.6. Actually, no, it wouldn't be this. Actually, we can use the mass of the fuel ejected. So they're using 30 kilograms of fuel. So 30 into the velocity at which the ions are ejected, 5.2 to 10 to the power of 4. This momentum, the momentum of the fuel ejected, is equal to the momentum of the spacecraft. The spacecraft's new mass will be 710 because it was originally 740 plus the fuel. Now it's 740 minus the fuel used, so 710 times the Vmax, the maximum velocity. Now if we solve for this, we 30 into 5.2 into 10 to the power of 4 over 710, sorry, that gives us the V maximum. And if we put this in our calculators, we would get 30 into 5.2 into 10 to the power of 4, 710. We're getting the maximum speed of the spacecraft to be equal to 2197 meter per second. And if I rewrite this, I can just say 2.2 into 10 to the power of 3 meters per second. That's scientific notation. Okay, so you have to always consider the significant figure. So that's the maximum speed of the spacecraft. Okay, next, outline why scientists sometimes use estimates in making calculations. Now this is a simple question. It's just using prior knowledge, using some common sense. We could say scientists use estimates because maybe it makes I don't know how I spelled that so bad. Makes equations or maybe calculations simpler, right? It makes them simpler. Calculations simpler. That's one good point. What else could we say? Maybe another point is that maybe some quantities in the equations are unknown. Some quantities are unknown, as they usually are unknown, because in lots of scientific experiments, lots of equations are unknown or quantities unknown, and we have to use estimates or approximations to calculate them. So some things might be unknown, or maybe just simply precision is not important in the experiment. Precision is not important. For example, maybe I spelled that wrong. For example, maybe they just want to get a general idea of the behavior of a certain object. So precision is not the most important thing. They just need to get the general gist of what would happen. So precision is not key. They don't need to be so accurate. So precision is not important. Right, these are some possible ideas for what you could give for the answer. You just need to make something up. It's not that big of a deal, these type of questions. These are some ideas. If you think of something else, you could use that as well. Okay, outline why the ions are likely to spread out. Now think about it this way, right? Ions, they're all going to be have the same charge, right? They have the same charge. Because they have the same charge, we know that like charges repel each other, and when they repel each other, they want to go as far apart from each other as possible. So for example, positive positive, right, they want to move away from each other, repel. Same thing with negative negative, they want to repel each other. So like charges repel, and so they spread out. This is some theory, but it's nothing that you wouldn't know. It's just simple. It's just they spread out because they're like charges attract, unlike charges like charges repel, unlike charges attract. So that's it, because they're same charges. Outline what effect, if any, this spread of ions has on the acceleration of the spacecraft. Simply, there is no effect, right? There is no effect on the acceleration of the spacecraft. There's no effect. That's it. You're just stating there's no effect. That's it. Why it might not affect is because the forces between these ions, do not actually affect the force on the spaceship. So if they don't have an effect on the force on the spaceship, acceleration won't be affected, of course. So these are two possible answers you could give for this question. They don't have an effect. The forces between ions don't have a effect on the force on the spaceship, and hence there is no effect on acceleration on the spaceship. Okay, this is some gravitational field theory. What is gravitational field at a point? So really, this is not a mechanics question in this one particular case, but you could still refer to your data booklet and figure it out. So gravitational field strength G is equal to Gm over R square, right? So all we have to say is that it is the gravitational force per unit mass on a small / test mass, and that is the exact definition for gravitational field strength. It is the gravitational force per unit mass on a small / test mass. And last question, Newton's laws of gravitation applies to point masses, meaning small masses. Suggest why the law can be applied to satellite orbiting spherical planet of uniform density. Now think about it this way. You have a massive planet, right? Maybe this is like 6.4 into 10 to the power of 23. This is the mass of Mars, okay? And then you have a small satellite, right? This could be like maybe 700 kilograms. Compare the masses to each other. Are they anywhere comparable? No, right? To this big Mars, or to the big planet, this satellite's mass is nothing but a test mass and nothing but a point mass. It's really not comparable, and hence that's why we can use this law for satellites orbiting spherical planets, because the masses are just not comparable. It's just so small. It approximates to a point mass. I'll just write the answer. Approximates to a point mass due to large difference. That's essentially it, right? planet is so big, the satellite is so small. The satellite is nothing but a point mass for the planet, and that's it. So that's your answer. Hopefully you've learned something. See you in the next video.